Okay, we're doing the circular motion practice problem. Is the second part of number 3. This one's a banked curve, but with friction, which is more or less the most difficult kind of circular motion you can do. So if you can nail this one, you're probably in pretty good shape. So again, we have a banked curve. I'm going to draw a nice big force diagram here. So there's my normal force. The weight, and I'm going 16 meters per second, which is faster than the design speed of the curve, which we found in the last part, which means if I'm going too fast, if I were to slip, if there were no friction, I would go towards the outside, which means that friction is pulling me towards the inside of the curve. And that friction is parallel to the track, therefore perpendicular to the normal force. So I'm going to we need to identify the acceleration direction. Still flat left. So we do have to break up two forces instead of one, but we don't have any choice in that because the acceleration isn't tilted. So I need to break up both F sub s and the normal force. I'm going to look and make sure my components balance. Yeah, it's pretty good. The vertical component here is longer than mg. Maybe I should make mg just a little shorter. But there's a downward component of the static friction force as well, so these three need to balance. And then we have two components going inward, which are taking us around the curve. So there's theta, and there's theta. I can't call the static friction force mu sub s n because I don't know that it's at its maximum value. So if we knew it was at its maximum or minimum speed, then we could say that, but we don't know that. And in fact, it's not. Positive towards the center of the curve, and I'll just arbitrarily choose up. Alright, F nets. So in the x dimension, I have n sine theta and F sub s cosine theta, and that has to equal mv squared over r. I choose v squared over r instead of 4 pi squared r over delta t squared because I'm dealing with speeds here and not period. In the y dimension, we have n cosine theta pulling up, or pushing up, static friction pulling down, down, and mg pulling down, and they have to balance. We're not accelerating vertically. So if I'm going to solve for F sub s, I need to eliminate n. So I'm going to solve for n down in this expression. And substitute it into the other. So you want lots of room here. And we want to distribute. I'm going to try to get away from fractions here, so I'm going to multiply the whole thing through by cosine theta as well. So multiplying through by cosine theta, we'll cancel this one, we'll square that one, and we'll put a cosine theta over here. And then I want to distribute here so I can collect all the terms with F sub s on one side. So I have mg sine theta plus F sub s sine squared theta plus F sub s cosine squared theta equals mv squared over r cosine theta. So I want to bring this mg sine theta term over to the other side. And on this side, I have F sub s times sine squared theta plus cosine squared theta, which simplifies nicely to 1. So F sub s equals, factor out an m, v squared cosine theta over r minus g sine theta. And I can put in numbers at this point. And we get 4,720 newtons. It sounds like a large force, but it's much less than the weight, which is 13,000 newtons. because the mass is 1,300 kilograms, which is good. The maximum static friction force is 90% times the normal force. We didn't really calculate the normal force here, but it's somewhat smaller than mg, I think, in this case. So again, we're well below that size. It's also a little bit less than the static friction force from the very first problem, where it was exactly the same curve at exactly the same speed, but the curve was flat, and we would expect that it would be less because the normal force is helping us make the turn, and before it was only the static friction making the turn on the flat curve. So it makes sense that it's a little bit less here.